When we're analyzing circuits, Ohm's law and Kirchhoff's rules are the main ideas that we're using to do it. We've actually been using both Ohm's law and the two Kirchhoff rules already. We just haven't really given a name to Kirchhoff's rules, and we haven't applied it in every situation possible so far. So Ohm's law we've talked about and we've used quite extensively. Kirchhoff's rules are stated in a number of different ways, but for the first rule, the rule about current says that if we look at some individual point, usually an intersection between a couple of wires or a couple of different components, we know that the current going into that spot and the current leaving that spot have to be equal to each other. So if, for example, we have, let me redraw that, say a couple of resistors that are all meeting at this spot, and maybe we have some current I1 coming in here, current I2 coming in here, and then current I3 leaving here, and current I4 leaving here. So we have current flowing in from these two directions and flowing out of these two. Well, we would know that the total current going in, so that'd be I1 plus I2, has to be equal to the total current leaving, I3 plus I4. Otherwise, we get this really rapid buildup of charge at this point, which doesn't make sense. You know, if the charge were building up there, we'd have very large forces, and the current would stop flowing in that direction. It would stop flowing toward that point if it couldn't get any more charges that way. So we have to have the currents be equal there. The other one that we have used a little bit is the idea that the total voltage, the total change in potential energy for one complete loop of a circuit has to be equal to 0. So if we have a battery, say of 12 volts, it doesn't matter what else happens around this battery, any path that we take to get around the loop, we have to have a drop of 12 volts. So if we go, say, in this direction, we take this branch like that, the blue has a total voltage drop of 12 volts through those three resistors. And if we took a different, say with the red, we ran it around this direction, there we go, and back to the battery. Even though it's a different pathway, different resistor we're going through, we still have to have a total of 12 volts dropped, because here we have 12 volts increased. So if we don't drop as much as we increase, then basically we're creating energy, and we've made an infinite energy machine, which would be useful, but not possible. So let's analyze this circuit. We'll solve for some unknown resistance using Kirchhoff's rules and the Ohm's law. So first off, we know the current at this one spot. We know all the resistors except this one. We know the current right here. It's always a good idea to start with the resistors, the components that you know the most about. So let's look at this situation right here. Now first off, if our current through this spot is 0.72 amps, 0.072 amps, that means the current all the way around to here is 0.072 amps, all the way until it splits up. Now here, maybe we'll call that I1, and here I2. But the rest of the way we have just 0.72 amps going through. Now, that current law, Kirchhoff's current law, would then say that I1 plus I2 has to equal 0.072 amps. Okay, so we can come back to that later on. All right, so back to this resistor that we know a lot about. We know that it has a resistance of 50 ohms and a current of 0.072 amps. So let's figure out the voltage then. So the voltage would be equal to, maybe I'll put this over by the resistor, so voltage would be 0.072 amps times 50 ohms, which would be equal to, That'd be 3.63. Oh dear. Come on back up. So 3.63. Oh, come on now. Okay, and up here, current for that guy as well. So voltage, it would be 0.072 amps times 100 ohms. So that would be 7.2 volts. Okay, sorry, I'm hitting lots of buttons here. Okay, so now we know that the voltage drop here is 7.2, the voltage drop here is 3.63, the increase here is 12, and we know that for any path that we take through here, the voltage drop has to be equal to, the total voltage drop has to be equal to 12 volts, because that's how much it's increasing by. So then for either of these, we can say that the voltage is equal to 12 minus 7.2 minus 3.63. 12 minus 7.2 minus 3.63, which is 1.17 volts for either this path or for this path. We have to have the same voltage drop for either one. So now on this one, the 20 ohm resistor, we know both the voltage across that and the resistance. And so we can solve for that I2. Switch colors here since we're looking for I2. So now, I1. So I1 will be equal to, well, let's see, V equals IR. So I would be equal to V over R. So that'd be 1.17 volts divided by 20 ohms. So 1.17 divided by 20 is 0.0585 amps. Okay, and we know that we had 0.072 amps coming in here. It splits into two paths, but the total amount doesn't change. So we know that I2, put a little space here, I2, we said those two have to add up to 0.072. So 0.072 minus the 0.0585 gives us it's 0.072 amps minus 0.0585 amps equals, and that is 0.0135 amps. Alright, so now we know both the voltage across this resistor and the current across this resistor, and so we can solve for our final answer. So we'll do red for resistance, so R, let's see, V equals IR, so R would be equal to V over I, which is 1.17 volts divided by 0.0135 amps. So that unknown resistor then is equal to about 87 ohms.